previous section, section 4.3, we've been discussing when are functions increasing and when are they decreasing. And that was something that was given to us by, we looked at the derivative and looked to see whether that was positive or negative. There's another property we want to take a look at, which is concavity, and as we'll see, that is a concept that's coming from not the first derivative, but the second derivative. So, what is concavity? So, examples here, I think I'm just going to do basically definition, at least in the first place, by some pictures. Here is a function that is concave up. It's bending up. And here is a function that is concave down. It's bending down. Now, we want to be careful that sometimes figuring out from a picture whether something is concave up or concave down is a little bit more subtle. You might not have a full going down and going back up. For example, I just draw this much of a curve. This is enough for us to see that it's concave up. Even though it's not going down and coming back up again, this is enough to show that it's concave up. Alternatively, here's a different stretch that's also concave up. If I were to draw something like this, we see it's concave down. We could extend it so it's bending down. Here's something else that's concave down. So these are all things that we want to be very careful with. So at this point, let's think about how we can make this more mathematically precise, rather than just saying bending up or bending down. And what we want to do is we want to think about slopes of tangent lines, as usual. So here we see that here's the slope of the tangent line here. It is very negative here. Around here, it's less negative. Now it's 0. Now it's positive. Now it's even more positive. So the slopes of the tangent line start off very negative, got less negative, made it to 0. Positive, more positive. We see the slope of the tangent line is increasing for a concave up function. For a concave down function, our slope of the tangent line starts very positive, becomes less positive, eventually becomes 0, and then becomes more and more negative. So what's going on here are, for a concave down function, our derivative, the slope of the tangent line, is decreasing. And so this is going to provide us with our definition, our formal definition of what concavity is. So we have a differentiable function defined on some interval. It's concave up if the derivative is increasing. It's concave down if the derivative is decreasing. So what we see here is that our concavity is, so we want to translate f prime is increasing. Well, let's think about what that says about the second derivative. The second derivative is the rate of change of the first derivative. And so if our first derivative is increasing, it has a positive rate of change. That's corresponding to the second derivative being positive. Whereas if the second derivative were negative, the rate of change of the first derivative would be negative. That'd be f prime is decreasing. So apart from just writing here in terms of f prime is increasing and f prime is decreasing, we can write out a test for concavity. So the book sets us off as a separate theorem. You could almost claim that this is the definition of concavity. So concave up means the second derivative is positive, and concave down is when the second derivative is negative. So to kind of summarize, the first derivative tells you, the sign of the first derivative tells when your function is increasing or decreasing. The sign of the second derivative tells you when your function is concave up or concave down. So let's just draw some pictures here with some different possibilities of things that could happen. So for example, if I wanted to say f prime, let's make a little chart here, f prime of x f double prime of x. So we can have 4 different possibilities. So let's assume that we have both of these here. So we want our function to be increasing, and we also want our function to be concave up. So that's how we have to draw a function that's increasing and concave up. F is increasing and concave up. Let's do another example. If f prime is positive but f double prime is negative, it's increasing but it's concave down. So something like this will have to do the trick. So it's concave down, but it is still increasing. So now if f prime is negative, but f double prime is positive, so now our function is decreasing but concave up. So something like this would be the case. And to finish off our chart here, if f prime and f double prime are both negative, our function is decreasing and concave down. And so something like this would be going on. So just from the signs of the first and second derivative, we can tell a lot about what our function looks like.